All right, great. So let's start with homework questions, and then we'll go over scalar potentials today. All right, homework. Question 3. All right. Okay, this was the divergence theorem question. On now? Okay. Oh man. All right. I'm sorry, everyone. Let me try turning the system off and turning it back on again. That might. Yep. Okay, there we go. Good. All right. Question 3 is about the divergence theorem, right? Or problem 4 is the question. The one you have a question on? Oh. I told you I was scatterbrained today. I was working on the homework solutions for that. That's why. Okay. In this problem, we would derive the electric field at a distance a from an infinite sheet of charge with charge density rho s. Assume that the sheet is on the z equals 0 plane. Yep. Calculate the electric field first using Coulomb's law, and then calculate the electric field using Gauss's law. So what is the trouble that you're having on this? Is just setting it up? It's a sheet of paper. It's an infinite sheet of charge that's on the z equals 0 plane. Yeah. Imagine a flat sheet on the xy plane. Right. The xy plane is the same as the z equals 0 plane. So the hint I'll give you for part A is that, we did this example problem with the infinite line of charge. You could go over that example in the notes and think about how we set that up, how we think about symmetry. and you're going to follow a similar approach for figuring out the electric field due to an infinite sheet of charge. The example that we did was an infinite line of charge. Yes. Yeah. Infinite sheet of charge. Imagine that there's a plane z equals 0. So on the basically the xy plane, and there's an infinite sheet of charge on the plane. Mm-hmm. Yeah, so there's two ways. There's two ways that you solve this problem. One is by integrating the electric field. That's the brute force sort of method. That's part A. And part B is where you use Gauss's law. When you use Gauss's law, then you have to define a Gaussian surface, where everywhere on that surface, the electric field is perpendicular to the surface, and it should be the same everywhere on the surface. Part 1C, what is the electrostatic potential of one of the protons? That's right. That's right. We'll go over today how you calculate that. That's going to be the topic of today. Are you talking about 1A? Oh, 2A. Okay. It will be in vector notation, right? Yeah. You can find a numerical solution if you'd like. You can find a numerical solution. You know, the electric field in decimal, you're going to have an x and y coordinate. Yeah. So, I mean, 2A is essentially like a problem. It's like 4 Coulomb's law problems. And then you have to add up the results from each one of those problems. That's actually why I added that little thing about using MATLAB to check your work. If you put in, if you put in the coordinates, I think, who had a question about this? Was it Justine you had a question about it? If you put in the coordinates of the points, remember when you're using Coulomb's law, you have to find that vector r, the vector r that's in between the charge, where the charge is, and where the observation point is. So MATLAB can be used, if you just do a simple subtraction in MATLAB, you can find that r, and then once you find the r, like calculating the electric field is pretty straightforward. So I would, it's part of your homework to use MATLAB to check your work and include the code. I think once you do this once, you'll see how easy it is to do some of these problems in MATLAB. Yes? Mm-hmm. It does still involve integration, but you'll see that it'll be much, much less work. It could be. It could be. I don't want to give away the answer, but yeah, when you have infinite when you have an infinite sheet of charge, it makes what? The way that you want to set up the problem, the way that you like to set up that problem is like, define a Gaussian surface, the charge is on the z equals 0 plane, right? And so you want to define some kind of surface where the electric field is going to be the same, uniform everywhere. And so there's two different surfaces that you could probably pick for that, and both ones will work fine. Yeah, I totally think I agree with you. It's the best way to do this problem. Hmm. The way you can set up the problem is assume that you're at some z coordinate, right? And that z coordinate defines how far you are away from the infinite sheet of charge. How Gauss's law works out. Yeah. Why do we talk about it after when we talk about after class? Because I don't want to go through all the steps to solving the problem. I want to get a chance to try it on the room. Yeah, just easy. Sure. Mm-hmm. Yes. Yes. Right. Yes. Oh yeah, absolutely. Yeah. The ring problem is a good problem because it allows you to really see the symmetry and why the x and y components of the field cancel, and you're only left with the field in the z direction. So the same concepts will apply in this infinite charge problem as well. Except now instead of a ring, you have just infinite sheet of charge. Yeah, no, I brought up a good point. When you have if you have something that's infinitely long or infinitely large, how do you enclose it with a Gaussian surface? The answer is you don't. If you recall what we did in the problem, the infinite line problem. Let me pull that up. There we go. Still have the notes up here. This was using Gauss's law to figure out the infinite line problem. So this line was actually an infinite line of charge, right? But we enclosed it with the cylinder, and that cylinder had some finite height h. But what ended up happening is when we set up the problem, the amount of charge enclosed in that cylinder had an h factor in it, and then the volume or the surface area terms also had an h factor, so they both ended up canceling out. So whenever you do Gauss's law problems, there's usually some kind of cancellation like that. Conceptually, what's happening is you're drawing a Gaussian surface and you're assigning it some factor h, right? Some height h, and that height h could go to infinity, right? Because you have an infinite line, but the h's end up canceling out. You're going to end up doing something similar for the sheet of charge, infinite sheet of charge. Yeah. So in Gauss's law, the strategy is that you have to enclose the charge that you have in your problem. Okay, you have to enclose it with a Gaussian surface. And what were the different characteristics of the Gaussian surface that we look for? If we're going to construct a Gaussian surface, what is it? Yes. Number one, the field should be perpendicular to the surface, every point along the surface. What's the second thing? If it should have identical value, because if the field is uniform everywhere, then you actually don't even need to do integration anymore. If you recall, like we did Gauss's law here, and we did a lot of these steps here, but in the end, what did we find? If we draw a Gaussian surface and the field lines are uniform everywhere, this integral just becomes the electric field times the surface area, right? So that's why we select a Gaussian surface where the field is the value of the field, the magnitude of the field is the same everywhere on the surface. So when you have a point charge, what's your Gaussian surface going to be? It'll be a sphere, right? And in the case of an infinite line charge, it's a cylinder. Infinite sheet of charge. You can't, but you can still use Gauss's law. Just like you have an infinite. That's right. That's right. You can't, just like you have an infinite line of charge, you can't enclose it completely, but you can still apply Gauss's law. There's a couple different options. Yeah, think about it. Well, I want to see what you all come up with on Wednesday. Because Wednesday, I'd actually like to go over the problems in class. Because I'll post the homework solutions online, but I won't be here to go over them with you the following week. So it would be nice if we just go over them on Wednesday. Should you enclose above and below? Yeah, for symmetry reasons, yes. And you have to the volume has to enclose the charge. Gauss's law says this. E dot ds is equal to q over epsilon. The flux on the surface of the volume is equal to the charge enclosed by the volume. Right? So the volume that you draw has to enclose the charge. Have I confused you, or does this help? Okay. Yeah, try playing around with it a little bit more. Again, like it's really helpful if you go over the example of the infinite line example again. You can go over that section and then as part of the lecture, and then see if you can apply the same ideas, the same strategy to the infinite sheet problem.
Okay, because I didn't think about it now. I was trying with the way with the approach on infinite line. I tried it with the ring. So that's what I see, because I knew it was flat and it was an infinite surface, but then I was looking at z is 0, so there's nothing protruding from it because that point is 0, so there's nothing there. That's where I got stuck at.
Well, yeah, it's you'll want to define a point at some distance away from the plane. Okay. You can use that as a starting point.
Okay.
All right. What else? What other questions do we have? Yes. Number 4. Suppose we have two thin concentric spherical shells of charge, one shell with radius A and the other with radius B. Okay. So what we're talking about here is a shell. Okay. So it's like the wall of a ping pong ball. The ping pong ball is hollow inside. And what we're assuming here is that these shells are so thin that their thickness is negligible. The thickness of the shells are negligible. And so we define a charge density on the on the sheet, on the surface of the shell. So the way it would look like this. I don't think my pen's going to cooperate today. Like this. One shell has radius A, the other one has radius B. Yeah, what the question is asking you, you're actually asked to find a relation, an equation for the electric field in 3 different regions. The first region is for R is less than A. So within this cell, the next equation that you're going to find is for R is less than A, A is less than R is less than B, so in between the 2 cells. And the third relation is for R is greater than B, so outside it. Yeah, so you're given. Well, it depends on what the values of rho S1 and rho S2 is. Yeah, so you're asked to put them in terms of rho S1 and rho S2. Yes. Yeah, you'll see that it's, well, look at the symmetry of the problem. You're asked to find the electric field at any point. So any point could be any r, theta, or phi, right? We're in spherical coordinates, so it could be any one of those. Any r, phi, or theta. But if you look at the symmetry of this problem, there's going to be spherical symmetry there, right? Yes. I'll give you guys a hint on this problem. Oh, the hint is there in the problem already. Use Gauss's law. You use Gauss's law, then this problem will become a lot easier. It needs a Q. It needs Gauss's the integral of E dot ds is equal to Q over epsilon, right? So your question is like, where does it? What do we use for the Q? That's basically what this problem is asking you. And there's the amount of Q is going to be actually different for part A versus part B versus part C. Mm-hmm. Yes. Inside of what? What shells? Inside the inner shell. Okay. No, you can't really do that, but there's actually there's an even more straightforward way of doing this problem. This is like one of those weird problems that's like if you don't want to overthink this one, you just apply Gauss's law and it will give you the relations that you're looking for. it seems kind of strange when you apply it because you're like, this doesn't make sense, but actually it does. I'll go over on Wednesday why it doesn't make sense. My hint to you to this problem is what I just said. Like if you just apply Gauss's law verbatim without even thinking about it, you'll probably get to the right answer. If you start thinking about why this works, then you'll become very confused. But it does work. Yes. Oh yeah, I'm sorry. It should be. They're both surface charge densities. Hmm. Thank you. Thanks for that clarification. Hmm. Yeah, you're going to be using Gauss's law in this problem. Yeah, that's what you can do in the homework. um, uh, I guess the hint that I would give you all is what I was just saying. Apply Gauss's law in each one of the three regions. I'm not going to tell you, but I just try either one. You'll see. You'll see which one will work. There's only one possible coordinate system you should be using in this problem. Try both. See what. Yeah. Other questions? Okay. So it's 8 o'clock right now. I would like to go over how to calculate scalar potential because there are some potential problems in this homework. And once we get through the scalar potential, then we can do more questions or we can just go on to some new material. Yes, I think so. Yeah, there's a lot of it. I mean, it's bringing in a lot of like vector calculus concepts, a lot of electrostatics concepts, and so on. So, all right. So we got to this point last week, right, when we were talking about potential energy. So let me just recap that real quick. We're talking about potential energy right now, and the analogy was that there's electrical potential energy is analogous to mechanical potential energy. Mechanical potential energy, we think about holding a ball up in the air, and as we drop that ball, that gravitational potential energy is converted into kinetic energy. By the time the ball hits the ground, its gravitational potential energy has converted to kinetic energy. Similarly, and the way that we found the total work, we said the work is the integral of F times dx. You're summing up, work is equal to force times distance, so you're summing up the force times the differential distances, and we're adding those up, and adding those things up means it's an integral. And so gravitational potential energy is mgh, mass times gravitational constant times the height. And with electrical potential energy, you want to imagine a similar kind of thing. You have an electric field, right? And just like it took some force to take that tennis ball and to move it against gravity, to move it a certain height, h, the same thing's happening here. If there's an electric field and you're moving this charge against the electric field, you're putting some work into the system, right? So a charge in the presence of an electric field, it actually stores energy. We will actually calculate how much energy is stored in the system later on in this chapter. But for right now, we're getting the basic idea of it. So if you have a charge in an electric field, just like if you're holding a tennis ball up in the air, there is a potential energy there. And that potential energy we found last time is equal to the differential Electrostatic potential is equal to dW divided by Q. It's equal to E dot dl. And the integral form, this is the one we're going to use more frequently. The voltage difference, the electrostatic potential difference between two different points is the integral of E dot dl times the negative. This one, I think, illustrates it in a much more clear way. So imagine that you have a point a point P1, and your charge is sitting here. The electric field is pointing down like this. If I take this charge and I move it to P2, is that going to take work, or is that going to happen on its own? Well, I should say, yeah. Is that going to take positive or negative work? Why will it take positive work? Why will it take work to move it to P2? Yes, exactly. You have to apply a force because the electric field is pointing down. Remember, positive charges like to go in the same direction as the electric field, right? So if we're moving this, we're essentially moving this charge against the field, moving it from P1 to P2. So yes, it's going to take some work to move it there. How much work? Yeah, go ahead. I'm sorry? Moving from P2 to P1 will actually be negative work. Because P2, we're moving the charge in the same direction as the electric field. See, the electric field is pointing from top to bottom. Negative work is energy released. Another way you can think about negative work is that just like the tennis ball, if you drop it from high potential, it goes towards lower gravitational potential, so it falls towards the ground. Similarly, like if you have a charge that's up here, the electric field lines are pointing down. So this charge, if the charge were up here and you let it go, what's going to happen? It's going to move, yeah, it's going to move down. It's going to move in the same direction as the electric field lines. Yes, it's not going to take work. If you release it from there, it would start moving on its own. This is the same idea as that parallel plate capacitor, right? You have, when you have this thing, movement perpendicular to the field does not take any work. Yeah. And in fact, that is all part of this formula. So here's, let's say you have your two plates. This one has positive charge. This one has negative charge. And then you put a positive charge here, right? The electric field lines are pointed this way. If I release the charge at this point, it's going to move in the same direction as the electric field. Charges move in the same direction as the electric field. Positive charges do. So you'd release it, it would move towards the negative charge. And as it gains kinetic energy, the scalar potential energy, the electrical potential energy is being converted to kinetic energy. Okay, so if we want to find the difference in electrostatic potential, we use this formula, V2 minus V1. So this is the voltage at point 2 minus the voltage at point 1 is equal to the negative integral of E dot dl, and that integral is taken from P1 to P2. And what's interesting about this is in this formula, it says you have to take a line integral from P1 to P2. There's so many different ways we can get from P1 to P2. You could just do a straight line like this. You could go across and then up. You could go up and then across. You could take any path from P1 to P2. Regardless of what path you use, the potential difference you calculate will still be the same. That's the funky part of this. This is because the electric field, when it's conservative, it doesn't matter what direction it doesn't matter what line you go on. The difference in the potential between the 2 points is still the same. Yeah, you could define your line integral going directly this way and then going up this way, or you could just define a line going straight from point 1 to point 2. So we'll do this example now. So suppose we have an electric field, x times ax minus 2y times ay. What is the potential difference between these 2 points? P1 located at -2, 0, 0, and P2 located at 5, -1, 3. Correct. So I'm just going to put down the formula on the board here. V2 minus V1 is equal to the negative integral from P1 to P2 of E dot dl. So I'd like everyone to give this a shot. And if you get stuck, we'll discuss it. I would like everyone to kind of get to the point where you get stuck. And if you don't, and if you're able to figure it out, that's great. Yeah. Yeah. I sometimes use those interchangeably. Sorry for any confusion there. AX and AY, those are the unit vectors. X hat, Y hat. The key part here is how do you get from P1 to P2? How do you set up that line integral? And you may or may not remember how to do this. Yes. For DL. Yeah, and when you're in, I'll go over it, but yeah, for DL in a Cartesian coordinate system, DL is always equal to dx, dy, dz. But then you may have to substitute values for those. But the dx, dy, dz is always the starting point. The hint that I'm going to give you is that, to get from, if you're doing the line integral directly from P1 to P2, like a straight line between them, you have to figure out the vector in between them. And then you have to come up with an equation that describes the line connecting the 2 points. And that line, if you remember from one of our homeworks, has to be three-dimensional line is often described in terms of a parameter. Isaac's shaking his head. She's like, oh, damn. How many of you all remember parameterization? Kind of, sort of. Okay. This is a problem where you have to do parameterization. All this stuff is coming back. Okay, so why don't we just we'll work on this together, because I think that I think many of you don't remember how to do it, which is okay, because I hadn't looked at this stuff in several years and I had forgotten how to do it too. So it's fine. So the potential difference between P1 and P2. So we have to do this line integral. V2 minus V1 is the integral of P1 to P2 of E dot dl. So I'm going to show you this just as a review. This is a point slope form for a three-dimensional line, a straight line. Okay, so it gives you a way to define a three-dimensional line in terms of a parameter t. So first of all is the vector between P2 and P1. If you want to get from P1 to P2, you subtract P2 from P1. And then you set that equal to B, B1, B2, B3. And then the equation for the line ends up being X is equal to A plus T times B1, Y is equal to A2 plus T times B2, E is equal to A3 plus T times B3. It might be more intuitive if I this out. Explain it a little bit. So let's say we have some arbitrary point P1, arbitrary point P2. So we'll call this doing a line integral. Line integral using parameterization. All right, so we want to take a line integral going from P1 to P2. And probably the most efficient way to do it is just to draw a straight line connecting the two. So the dimensions for P1 in this case were negative 2, 0, 0, and P2 was 5, negative 1, 3. All right, so how do we get from P1 to P2? Because we're going to be integrating from P1 to P2. We want to define the equation of a line going from P1 to P2. What is an equation for this line? We can define this line in terms of a parameter, okay? And I'll explain to you how that works. First of all, the first thing we're going to do is we're going to find the vector that connects the two. Let's call this vector R, since that's what we've been calling it in the past. What is an equation for R? R equals what? Very straightforward way to find that one. P2 minus P1. Final minus initial, exactly. So I'll just even put that down. Final minus initial. So that's P2 minus P1. 5, -1, 3, minus -2, 0, 0. So what does that leave us with? 7. So we're going to put this as a vector now. 7, -1, 3. Okay, so this is the vector connecting the two. So we want an equation for this line. So imagine that we have a line that's defined from here to here. That line could also continue in this direction and that direction. The way that we can define an equation for this line is to use parametrization. So this is the initial point. P1 is the initial point. So if we do P1 plus some parameter t times the vector r. All right, so that means, let's say I took, just showing you intuitively how this is happening here, P1 times 1 times r. So if t is equal to 1, what is P1 plus r? Where is that going to take us? So you start off at P1 and then you add the vector r to it. It's going to take you to P2. What is P1 plus 2 times r? It just takes you twice as far. I'm sorry? I think it's -2. It's -2, yeah. There's a negative sign there. Sorry about that. All right, everyone with me so far? So this serves as an equation for a line. P1, the first point, plus a parameter t times the vector that connects P1 to P2. I'm sorry? R is the direction from P1 to P2, right? I'm sorry, let me just write this more clearly. P, so we can write some arbitrary point on the line is equal to P1 plus a parameter t times r. So that generic point P, we can just say x, y, z is equal to, this is, we're going to put in the coordinates for P1 here. So -2, 0, 0, plus t times 7, -1, 3. Right, this should be parentheses. All right, so this is our equation for the line. Any questions? Are there any questions how we got this? What I showed you in the notes is a generalized form of this. Like if we want to separate this into 3 equations, we could say x is equal to -2 plus 7t. Y is equal to 0 plus or minus t. Yeah, you got it. Z equals 0 plus 3t. All right. Again, everyone with me here? Okay. This is a really easy way to parameterize a straight line. If you have 2 points in space, and I tell you, give me an equation for that line, this is how you do it. Use a parameter. And these parameters can actually get pretty complicated. I think you've seen in one of your previous homeworks, I gave you the equation for a helix. That's in terms of a parameter t. So when you do three-dimensional line equations, you can actually get some pretty crazy shapes by using parameterization. But this is a very simple example, which is just a straight line. Okay, so this is an example of how you actually do it, and the notes gives you the formal definition of it. X, Y, Z is equal to A1, A2, A3. This is your initial point. This is your P1, plus the parameter T times the vector connecting P1 to P2. So this B1, B2, B3 is the vector connecting, going from P1 to P2. Right? So that's what this is. Now that we've figured this, out, now we do the line integral. All right, just to remind everyone, when you do the line integral, we are looking for the V2 minus V1. V2 minus V1 is equal to the integral from P1 to P2 of E dot dl. Whenever we have a line integral like this, or a surface integral, or a volume integral, we break it down into the individual parts. We know that this is the dot product between the electric field and dl. So first we define what dl is. What's an equation for dl? Yes, yes, we will get to that. I'm just trying to go from, just do the step-by-step process. I want the step-by-step process that works every time, regardless of the problem. If we're in the Cartesian coordinate system, dl is equal to dx, dy, dz. And now we have to substitute values for dx, dy, dz based on what line we're on. So these equations define what line we're on. So what is dx going to be? Close. You're missing one little thing. 7 dt. Yes. So dx is equal to 7 dt. dy equals minus dt. dz equals 3 dt. So this now is very convenient because our dl is now, the whole thing is in terms of this variable t. 7 dt negative dt 3 dt. So everything is in terms of t now. So what is our electric field? So let's see, the electric field that's given to us, x times ax plus 2y times x times x hat minus 2y times y hat. X times x hat plus 2y times y hat. When you're doing line integrals, it's a single integration, so you want everything in terms of a single variable. So our dl, we put everything in terms of t, in terms of dt. So we have to do the same thing for the electric field here. We've already defined and equations for x, y, z, and also dx, dy, dz. I'm sorry? Is it minus 2y? Thank you. Thank you. All right. So x is equal to negative 2 plus 7t. Negative 2 plus 7t times x hat minus 2 times, what's y equal to? Y is equal to negative t. Y hat. All right, so all I just did is substitute the values for t there. And E dot dl is this quantity divided with this quantity. All right, so you multiply the x components together. What do you get there? It's 7, what is it? I'll just write it down. Negative 2 plus 7t times plus the y components. Oh, it should be dt plus the y components, negative dt and 2t. So minus 2t dt. Everyone with me? So E dot dl is negative 14 plus 49t minus 2t, and this is all by dt. So I got negative 14 plus 47t. Does that sound right? Is that what everyone else got to? Great. So that was the more complicated part. Now the rest is just integration. When you're going from P1 to P2, what's our limits of integration? We put everything in terms of t. Yes, why is it going to be 0 to 1? That's how we define t. All right, in order to go from P1 to P2, t is going to go from 0 to 1. Because remember, when t is equal to 1, when this is equal to 1, then you're basically going from P1 and you're adding this vector r to it. You're adding 1 times that vector r. So that will take you to P2. So as we're going from P1 to P2, we put everything in terms of t. So our limits of integration also has to be in terms of t. So t equals 0 to t equals 1 of E dot dl, and that's E dot dl is negative 14 plus 47t. All right, so this then becomes negative 14t plus 47 over 2t squared, going from 0 to 1. Negative 14 plus 47 over 2, 23 and a half. My brain is foggy. What is the final answer here? Okay. 59. Okay. Does everyone see how to do that problem? If you had a similar problem in cylindrical coordinates or spherical coordinates, I would expect you to be able to do that because it's just the same procedure we're applying every time we do a line integral. And it turns out, yeah, just a sec. It turns out that if we were to take a different path, like if we went like across like this and then up, or if we took a curvy path, or we took a totally crazy, weird path, and we still ended up at P2, the value of that integral would still be the same. This is a property of electric fields. Yes, absolutely. Yes, Justy. Yes, it is. Good question. The unit should be in volts. What's that? Well, yeah, it'll be negative. Okay, so there's your example of a simple line integral to find the electrical potential difference. Now we're going to do a problem where we find the electrical potential due to a single point charge. So this is another thing that I would like everyone to just try on your own and see if you can figure it out. What we're doing now is we are applying this formula, which is also up on the board. V2 minus V1 is equal to integral from P1 to P2, E dot dl, and there's a negative sign there. But this time we're doing it with, imagine that we have a point charge Q. So we have charge Q here. This is your observation point A. We want to find the potential at point A due to this point charge. And the way that you can do it is by setting up V2, this potential here, we can call this P2, and we can call this one P1. So here's a question. What's the potential at P1? This is an infinite distance away from Q. So P2, this is P2. P2 is pretty close to the charge. And then P1 is infinitely far away. So if it's infinitely far away from the charge, what's the potential going to be? It's going to be 0. The closer you move to the charge, the more electric field there is, right? Let's go back to the basics. Wherever you have a charge, electric field is radiating out from there, right? The closer you are to that charge, the more electric field you have. The more electric field you have, what does that do to your potential energy? It increases it. It's like if you have more gravity and you're holding the ball at the same height, that means you have, like, if there's more gravity, then there's more gravitational potential energy, right? So point charge generates an electric field. The closer you are to that point charge, the more scalar potential you're going to have. So A has some scalar potential because it's at distance r away from there. And this other point, which is infinitely far away, that has basically 0 potential. So why are we doing this problem? Because this is a derivation. This is a derivation for the electrical potential at the point A. So what is the potential at some distance r away from a single charge? So using this integration, see if you can figure out a formula for that. I'll give you all a few minutes to try it. You can start off with this formula, and I gave you a hint already. The voltage at V1 is going to be 0. So the second hint I can give you as you're figuring out this problem is E dot dl. So this problem doesn't tell you what E is, but you know what E is from before. Remind yourself, what is the electric field from single point charge? You can look back at your notes for that. Is it setting up the problem? Which part are you all stuck on? Setting it up? Oh, okay, okay. Well, I can certainly back up and show you that equation if that helps. This is the generalizing Coulomb's law, and this was that first example of Coulomb's law. This is the formula, the electric field from a single point charge. Yeah, 4 pi epsilon r squared. The way you can remember that, by the way, is you know the surface area of a sphere is 4 pi r squared. That's where that term comes from in the denominator. Four-thirds pi r cubed. That's a good question. DL, so another hint, you can work in spherical coordinates for this problem. If you work in spherical coordinates, it will help, because the Coulomb's law, this is basically in spherical coordinates. Sure. If you're not able to figure this out, don't feel bad. It's just trying. Like I feel like the more you try and just kind of like explore a little bit, then you just end up thinking about things and thinking about those things. Even if you don't get the right answer, you end up learning the stuff a little bit better. That's why, like, when you struggle on the homeworks, the more you struggle on it, the more you're actually learning from it. Did you say it has 3 components? No. This one's in spherical coordinates, so it'll actually just be in terms of the variable r. Mm-hmm. In this problem, yeah, everything's along one vector. Absolutely. Shall we go over it real quick then? You set up this V2 minus V1 is equal to integral of P1 to P2 dot E dot dl. This is P1 and this is P2. We want to find the difference in potential from here to here. So VA, V of the observation point minus V of infinity, so this is the point that's infinite distance away, is equal to this integral here. So as we were just talking about, you can set this up in spherical coordinates, but you really could do it in any coordinate system you want. But it's convenient to do it in spherical coordinates just because, you know, the Coulomb's law is defined in spherical coordinates. So this E dot dl, the dl is equal to r hat times dr. Why? Because we're going from P1 to P2. We're going from this point to this point. And this is all along the same line here. So we are moving from this point to here. So this is the r hat vector is in this vertical direction here. R hat points from where the charge is to where the observation point is, right? And this is all in a straight line here. So dl is r hat times dr. Yes, question. So A is at r, right? Mm-hmm. At some distance r, yeah. So the dl becomes r hat times dr, and the electric field, we can set that equal to the radial electric field component. Okay, and this is where it's going to like match up with Coulomb's law. So VA minus 0 is equal to the integral from infinity to r of E dot r times dr. What we're trying to do is solve for E sub r. So in this next part here, what we do is VA is equal to the negative integral from r goes from negative infinity to r of q over 4 pi epsilon r squared. So this is Coulomb's law. I'm sorry. I goofed something here. We're not trying to solve for E sub r. We're trying to solve for the potential. Sorry, my mind's on the last chapter. We use Coulomb's law to find E sub r. We're interested in, we're deriving the scalar potential of this point charge for this problem. All right, so this E sub r is equal to q over 4 pi epsilon r squared. This is Coulomb's law. And then we have to integrate that from r is equal to infinity to r is equal to r. So this is r equals infinity. This is r is equal to r. And so we're integrating from this point to this point, like we should be. Q over 4 pi epsilon r squared. And when we take the integral of r squared, we get 1 over r, evaluated from capital R to infinity. Notice what I'm doing here again. I'm taking the lazy approach. If I were to be mathematically rigorous, instead of just throwing in an infinity here, I would do the limit as something goes to infinity, as the variable goes to infinity of this equation. As engineers, sometimes we just like to throw in that infinity there. So then you're left with 1 over capital R minus 1 over infinity. So this 1 over infinity goes to 0, right? That term becomes negligible. Yep. And then you're left with q over 4 pi epsilon times capital R. Capital R is the distance between the two. All right, so let's compare this to Coulomb's law. Coulomb's law says the electric field is equal to q over 4 pi epsilon r squared. The scalar potential, the voltage, is q over 4 pi epsilon r. It's a very similar equation. Just it goes to the r squared now becomes an r. That's the major difference. Yeah, you can. You can. So what does this mean then? Okay, like just so we're all on just so we're all on the same page here. If I have a point charge here, if I have a point in space, and I want to know how does the scalar potential change as I'm moving away from that point. Okay, so if this is r, the distance away from the charge q, I'm going to have a situation where this drops as 1 over r. The scalar potential, so this is the scalar potential v, drops as a function of 1 over r. It also implies that as I get closer and closer to that point, the point charge, what happens to the scalar potential there? It goes to infinity. Q over 4 pi epsilon r. As r goes to 0, the scalar potential goes to infinity. It gets very, very high. So at that point is what we call it a singularity, because at that point the scalar potential is infinite, so it's undefined. But some minute distance away from that, the scalar potential is still defined. All right, just keep that in mind. And this goes for electric field calculations too. Coulomb's law. Coulomb's law is, let me back up here. Q over 4 pi epsilon r squared. So again, when r is equal to 0, you have a singularity. The electric field goes to infinity. All right, good. Moving on then. So that's the electric potential due to a single point charge. Simple formula. V is equal to Q over 4 pi epsilon r, where r is the distance between the point and the observation point and where the charge is located. Do you remember how we had this set of formulas for the electric field also? If you have a single charge, you had a certain electric field. If you had multiple charges, you had to sum up the contributions of each charge. That's like the problem in your homework. You could sum them up. You can do the same thing with the scalar potentials as well. This is the equation for a single charge. This is the equation for multiple charges. You will find that calculating scalar potential is easier than calculating electric fields. Because with electric fields, you guys had to calculate the vector connecting the observation point to the charge. Pain in the butt, because if you have different charges, that means you have 4 different vectors that you have to figure out. The nice thing with scalar potential is that there's no vector. It's all scalar calculation. One of the reasons why we actually even define scalar potential to begin with, and why we like using scalar potentials in electrostatics, is because if you do your calculations in scalar potentials, it's a lot easier. Once you know what the scalar potential field is, you can figure out the electric field fairly easily. Does anyone know how you can do that? You will know. We'll go over it, but the hint is this. Oh wait, no, that's not the hint. That is it. V is equal to the integral of the electric field, and E is the gradient of V. So once you have the scalar field, just take the gradient of it, you got your electric field. You can actually do these types of things in MATLAB nicely. We'll have some, I'll show you some examples, if not today, one of the other class periods, where if you just calculate the scalar potential in a 3-dimensional space, then you just take the gradient of it, you can plot that vector field and you show the electric field everywhere. Easier to calculate. All right, so here we go. Electric potential due to single charge, electric field due to, Scalar potential due to a single charge, scalar potential due to multiple charges, scalar potential due to charge distributions, just like before. If you have charge distributions, you have to integrate that charge in order to find the scalar potential at a given point. Again, I will say that these charge distribution formulas are easier than the electric fields because there's no vector quantities involved. So in the last 10 minutes, I think we'll have enough time to try this problem. Suppose we have a disk with radius b, uniform charge density rho s. Calculate the electric potential along the axis of the disk. Keep in mind, this problem is not asking you to calculate the potential everywhere in 3D space. It's only asking you to calculate the potential along the z-axis. All right, so once everyone has that formula down, I'm just going to put this up on the board. So V is equal to 1 over 4 pi epsilon, rho s over r ds. Why are we using that formula, by the way? Why are we choosing that formula? The surface charge, right? Yes. So you can start off by drawing the geometry or imagining in your head what it looks like. It does help to draw it out. Then put the observation point, draw in the observation point on your graph. And see if you can figure out a formula for the electric potential. Yeah, the disk is on the XY plane. So, if this was your three-dimensional space here, your disk is sitting here on the XY plane. That being said, this problem should be done in cylindrical coordinates. It'll make your life a lot easier. Oh, actually, I take that back. You don't have to do it in cylindrical coordinates. But okay. Oh yeah, sure. The disk has radius b, uniform charge density rho s. Exact, the location of the charge. Remember, integration is where you're kind of like adding up the contributions of all the charges, right? So when we do this, V is equal to 1 over 4 pi epsilon integral of rho s divided by r. we are summing up the contributions of all these, all these little points on the surface. If you imagine this surface is, oh, that's not good. This surface has all these charges on it. We're adding up the contributions from each one. So we can work through some of this. So let's say we have some kind of observation point, and that observation point is at a distance z. We can just call it z. Away from the sheet of charge. And the disk has a radius b. So this is b. So the hint is you have to add up the contributions of all those charges. What would be the logical next step here? Let me just erase some of these charges to make it less cluttered. Okay, yeah, we can start with that. Yes, there's symmetry. There's certainly symmetry in this problem, but the nice thing about scalar potential, as I mentioned earlier, is that you don't have to deal with these directions of electric like you have to do with electric fields. With electric fields, we have to figure out a radial component, an axial component, a z component. Here, we don't need to worry about any of that stuff. So V is equal to 1 over 4 pi epsilon double integral of rho s divided by r times ds. Okay, so good. We can start off by figuring out what ds. What is ds in this case? Now keep in mind there's no dot product. Ds is not a vector quantity. Ds is just a scalar. R d phi dr. Correct. So one of the just subtle differences between when you're doing these electric field integrals versus when you're doing scalar potential integrals is scalar potential, everything's scalar. There's no vector quantities to really worry about. No dot products involved. What's that? Oh, okay. Yes, let's go over that. Why is it? We're integrating a surface charge, right? So if you imagine all these charges on the surface of this disk, what are the two variables that we have to expand, or the two variables that we have to span in order to cover that whole circle? What are the two coordinates? R and phi, exactly. So that's why our ds is going to be r d phi dr. Our limits of integration, r is going to go from what? 0 to what? 0 to b, right? We're going to integrate from r is equal to 0 to b. And how about phi? 0 to 2 pi. Good. All right, so we figured out ds. We figured out our limits of integration. Now, how about r? Yes. So let's pick an arbitrary point on here. All right, we have to integrate the entire surface, but let's pick an arbitrary point. So this point here, we want to find the distance from this point to, let's draw that. We want to find the distance between z, the observation point, and where the charge is. Right? We're saying we're trying to find the contribution of the charge at this point, and the observation point is out there on the z-axis. So we can draw our little triangle here like this. right? So this is obviously a right triangle. The distance here is z. The distance here is r. And so what's the distance from the observation point to the charge? Exactly. Square root of z squared plus r squared. Right. So this r, the distance r, is equal to the square root of z squared plus r squared. Now, rho s happens to be a constant, so we can just take that out of the integral. Rho s over 4 pi epsilon. We determine our limits of integration. R is going from 0 to b, and then phi is going from 0 to 2 pi. 1 over r. So r is equal to the square root of z squared plus r squared. And ds is equal to r dr d phi. All right, so this is the integral that we have to solve. Oh, yeah, that can be a little bit confusing. Yep. Remember what all your variables mean. All right, we're almost running out of time here, so let's quickly finish this up. Rho s over 4 pi epsilon. This d phi, notice that there's no phi variables in here. So this d phi can kind of come out of the equation. So phi is equal to 0 to 2 pi. This d phi term can come out there. And then you're left with this other integral, r equals 0 to b of r dr over square root of z squared plus r squared. Now, the way you solve this integral, 4 pi epsilon times 2 pi. So this is, let's see, this becomes just z squared plus r squared square root. All right, because your u is equal to z squared plus r squared. Du is equal to 2r. So the form of this integral is u to the negative 1/2 Yeah, this one is actually on the table of integrals. It just comes out to z squared plus r squared. So just because we're almost out of time here, let's not belabor that point. So this goes from 0 to b. So the 2 pi cancels here. You're left with 2 here. So rho s over 2 epsilon. You're left with z squared plus b squared minus. The next term is you're subtracting the 0, so it's z squared plus 0 squared, so you're left with the square root of z squared, and then this is just z. Okay, so this is the scalar potential from a disk. So notice how much easier these problems were. So if I asked you, let's say I asked you, say, hey, figure out the electric field along the z-axis. One trick you could do is say, hey, I'm going to figure out the scalar potential first, and then just take the gradient of that to figure out the electric field. Different ways to skin a cat, right? Okay, thanks for your attention. Homework will be due at the beginning of class on Wednesday, but we will go over homework in class so that it's a way for you to prepare for your exam. Yes? No, I haven't made the exam yet.